You just heard delay lines and various types of comb filters to form a digital delay that's running on custom hardware for a delay guitar effect. In this video, I'd like to discuss the basics of delay lines and comb filters, and then also how we can implement them on a digital signal processing system such as the one you're seeing on the bottom right. Throughout, we'll look at examples in C code and how to implement that on an STM32 based DSP platform. The reason we are looking at comb filters and delay lines is because these basic structures and filters form the basis of many different digital effects, such as delays, reverbs, flanges, and so on. We will look at delay lines first, as delay lines are very simple, but form the basis of comb filters. Once we've covered delay lines, we will look at comb filters. There are two types of comb filters we'll see. One is an IIR, so infinite impulse response, which is a feedback type comb filter, and an FIR, so finite impulse response feed forward type comb filter. In this video, again, we'll look at the delay line basics, and we'll only look at FIR comb filters to start with. Then in future videos, we'll continue with IIR or feedback comb filters, which are slightly more involved, and then look at how to implement full digital delay algorithms, reverb algorithms, and so on, where you can really be creative and create your own audio processing effects. Again, all this theory we will accompany with real-time software implementation in C. We will look at frequency responses, time domain behaviors, and how to get this up and running in real time. A huge thank you to PCBWay for sponsoring this video. The hardware we'll be using in this video was manufactured and assembled by PCBWay. This is again a custom digital signal processing platform for guitar. I'll leave a link to them in the description below, but make sure to also follow them on Instagram to check out all the cool new designs they're producing. If you're interested, I have a whole DSP playlist on my channel where I show how to create your own effects such as digital overdrive algorithms, but also cover the basics of DSP such as FIR filter basics, IIRs, Z transforms, and so on. A link to this will be in the description below. Before we can look at comb filters, we need to cover the basics of delay lines. Delay lines are used in many different time-based or time-varying effects, such as delays, reverbs, and so on, and as we'll see, we'll need them for comb filters. As we're implementing this in software, we are looking at discrete time systems. So we're working in terms of samples, not in terms of continuous time. That means we'll have an ADC and a DAC, and I'll show you briefly the hardware just a bit later, but that means we also have a sampling rate or sample rate, fs, which is in hertz. So we sample, for example, for audio 48,000 times per second, or at 48 kilohertz. The delay line in discrete time effectively takes a sample at its input, so x of n, feeds it through the delay line, and produces an output, y of n, which is simply a delayed version of the input. The output is exactly the same as the input, except the output is delayed or phase shifted, so to speak, by a number of samples. In this case, we'll say that k is the number of samples the output is delayed by. We can work out, given a time delay, td, for example in seconds. For example, if you want a 1 second time delay, so td equals 1, we have a sampling rate of 48 kilohertz, then we need to have k equals to 48,000 to get a 1 second delay. Now k, the number of samples we shift by, can either be an integer, which is very easy, or a fraction, where we'll need to use interpolation. For now, we will just be using integer multiples of k. So for example, if we feed in a pulse, so simply at sample n equals 0, we have a single pulse up to a certain magnitude, and after that we have amplitude 0. If we feed that into our delay line, at the output we'll get all zeros, and then k samples later, we will get a pulse, which is equal to the magnitude of the input pulse. So very simple, we are simply shifting the input to the output by a certain number of samples. Let's immediately see how to implement this in C using a circular buffer. As you'll see, this is very simple. This is a picture of the hardware we'll be using. I have a few other videos going through this in a bit more detail. Effectively, we have an STM32 microcontroller in the center, which can interface to a host via USB, as well as serial while debug for programming, and has various control settings on different boards, as well as dip switches. This STM32H7 is hooked up to a codec, so this contains audio quality ADCs and DACs, and that codec then on the other side, on the analog side, connects to an analog front end. So we have an input, a mono input, and a mono output in this case. So we can take an input signal, feed it through the front end into the codec, it gets digitized, processed by our STM32H7 microcontroller, sent back to the codec, converted to an analog signal via the DAC, fed through the analog output front end and to the output jack. In Altium Designer, just to visualize where the jacks are actually on the bottom side with these foot switches and some LEDs, because this then fits quite nicely into a guitar pedal enclosure. Again, please make sure to check out the DSP playlist. In particular, I have this video on setting up the STM32 with I2S and DMA, as well as double buffering, so I won't be going through this in this video. And that's video number 55. We will be using circular buffers for this delay line because this is quite an efficient method of storing our delay samples. Make sure to check out video number 17, which is on FRR filter design, which also goes over the theory of circular buffers. Moving over to our software side, I'm using STM32 Cube IDE to program these STM3287 microcontrollers. In my project, I've created a separate delay line header file and a delay line source file, and you'll see these are very, very simple. To start off with, I need some sort of container for my delay lines because in future, in our reverb and delay algorithms, we might need several of these delay lines. To do so, I have a struct. In this struct, I store the length of the delay line, so how many samples it can store as a maximum, for example, up to k samples, as well as the circular buffer variables. This includes the index of the circular buffer, as well as the buffer itself, the memory, so to speak. For static memory allocation, I'm just defining this value at the top here, which is the maximum delay length of any delay line in this particular system. And so I can just immediately initialize. Of course, this isn't great because it immediately allocates the maximum amount of memory, even though we might be using a shorter delay line length. But for the sake of simplicity, we'll just keep it as this for now. We then need two functions for this struct. One is to initialize the delay line. This will compute from the delay time in milliseconds we pass through it, as well as the sample rate in hertz. It'll compute the length of the delay line, as we saw before from our formula, as well as clear the buffer in the delay line. Secondly is our main function, which is the delay line update function. This will take an input and produce a delayed output. And the input and outputs are all floating point variables for simplicity. The .c source file for the delay line is very simple. Again, we have the initialization function, which takes in our struct, the delay time in milliseconds, and the sample rate in hertz. First of all, we want to compute the delay line length, so we convert the delay time in milliseconds to seconds, and then multiply it by the sample rate in hertz, and we round that simply by casting to an unsigned int. And this is our delay line length. If the delay line length happens to be longer than the define, we simply clamp that. Then we loop through the buffer, clear the memory, reset the array to 0, and then also clear our circular buffer index. So very, very straightforward. Our update function is very simple as well. Keep in mind, this is a very simple implementation. You could, of course, write this much shorter, but for the sake of clarity, I've expanded every single line and showing what's happening step by step. Again, the update function takes the struct, as well as an input value as a float, a single sample, and returns a float, again, a single sample. The first thing we want to do is read from the delay line, and that will be the current output of the delay line. So we're accessing memory at the circular buffer index and setting that to an output variable. Then, because we've now saved that output value in a different variable, we can overwrite the delay line at that current index with the new input, which will then be used in k samples time. Once we've stored that, we can increment the delay index. Then we check if we need to wrap the circular buffer. So if you've reached the maximum length of our delay line, if we have, we start at the beginning again, and then finally we return the delayed output. So if your delay line is variable, so if you're constantly changing the length, of course you'll have to change some parts of the structure because you of course could create a variable delay. Then you have to make sure, for example, the wrapping still works correctly and you don't get any glitches when changing. So keep in mind a very, very simple static implementation, so to speak. But that's all we need basically for this simple delay line. In the main.c code, all we have to do is then include the delay line header file. In the case we just want to use one delay line, we create one struct. In int main, we can simply initialize our delay line by passing the struct by reference. We can start off with, for example, a 500 millisecond delay and our sampling frequency, which I've defined before. In this case, it's about 192 kilohertz. So it's a half a second delay line. Then in my ADC callback, once I'm processing all my samples, again, this is on a sample by sample basis. All I have to do is call the delay line update function, pass my struct, and pass my current input sample to get the current output sample of that delay line. So now let's look at the measurement setup and perform some basic tests. I've hooked up our bottom DSP board to power, so 9 volts DC, as well as this serial wire debug connection to my computer for programming. I'll be using my Analog Discovery Pro, which is a USB-based oscilloscope and function generator, where I have 2 oscilloscope channels, one to monitor the input, one to monitor the output, as well as one of these wavegen channels to produce my input stimulus, so we can produce sine waves, square waves, and also do frequency response measurements later on. My waveform software open, I have the wavegen enabled. Remember, we have a half a second, so 500 millisecond delay line set up. So what I'm doing is sending in a square wave with a period of 2 seconds so we can see what happens at the output. What we have to keep in mind though is that this is not a DC coupled connection. On this DSP board, I'm actually using AC coupling as I have to bias my op amps at half the supply voltage, so we do have this high pass filter at the input as well as at the output. This means for a square wave in, without any processing, we will simply see pulses out because we're effectively high pass filtering our signal. Now without the delay line enabled, without the effect enabled, we have our yellow trace at the top, which is our input signal, our 2-second period square wave, and at the output, this is without the circuitry enabled, so it's a direct true bypass feed through, we are getting a square wave at the output because it's perfectly just a wire connection. Now let me turn on the effect and let's see what happens. Now keep in mind, the high pass filter is now engaged, which is in hardware, it's this AC coupling. But what we see now are these pulses, and in fact these pulses are not aligned with the input signal square wave edges. With a pure AC high pass filter, the edges of the input square wave would produce pulses in phase with the output. However, now we have a half a second delay line. What we can see if we look at the bottom x-axis, we have 0 seconds as our center, and to the right of that, the large tick is 0.5 seconds. And that's approximately where our output pulse is, so it's a half a second delay. Anytime we get a pulse or AC transition on the input, our delay line shifts that by the amount we specified, in this case half a second, and we get a pulse at the output. So for a positive going square wave input pulse, a rising edge, we get a rising pulse, and then 1 second later on the downward transition on the input, again half a second later, we get a negative going pulse on the output. This is exactly what we expect. So we are delaying our signal by 500 milliseconds. Now let's go over to the guitar and see what that sounds like with just a delay line and what the effect is. Now we've seen the basics of delay lines and how simple they are to implement, we can move over to comb filters. And we'll see why they're called comb filters in just a bit. Again, comb filters come in various flavors. They can be feed forward or FIR filters as well as feedback, so IIR filters. In this video, we'll just be looking at FIR filters to start with. The FIR comb filter is a very simple structure. The block diagram is shown here in the bottom center. We have our input sample, x of n, that's fed through a gain stage, so that's a constant multiplication, alpha, fed into a summer, and then passed to the output, y of n. The output, however, also has a second term to it. If we follow the bottom path, we start at xn, our current sample, we multiply that by a different gain, in this case beta, and we feed that into this z to the minus k structure. This z to the minus k structure is simply our delay line which we saw previously, where again k is the number of samples we shift by, z is the Z transform operation, which we'll see in just a second. The output of this delay line is then summed with the current input times the alpha gain, and that equals the output sample y of n. This is very simple, and we can write a difference equation at the top. So our current output sample is equal to some gain alpha, which is a constant, times our current input sample, plus beta, which is a different gain, constant, times a previous output sample from k samples ago. And this is all this FIR comb filter is doing. We have 3 parameters to play with. These 2 gains, alpha and beta, as well as the number of delays we have in our delay line k. The nice thing about this FIR comb filter is that we're not particularly worried about stability. This is a FIR filter, which means it has a finite impulse response, means it's pretty much unconditionally stable. You can also straight away see that this is rather simple to implement in software, as we've already implemented the delay line. Keep in mind also, for now, we're just looking at values of gain, so alpha and beta, between 0 and 1. The question then is, how is this different to the delay line? Why do we need to use an FIR comb filter, and what are its special properties? First of all, let's think about what is the output for a pulse input. So if our input in discrete time is just a 1 followed by loads of zeros, what is the output y? Well, that turns out if we pass in the 1 and all zeros, we get alpha, then loads of zeros, and at k samples later, we get beta times 1 and loads of zeros. So it's effectively our original signal times the gain, alpha, plus 1 repeat, times the delay line gain, beta. So it's original signal plus 1 repeat. That's already kind of useful. It's a simple delay, which includes the original signal. The question is then, also, what is the output for sine input? Given that signals can be decomposed into sine waves, this is generally a good question to ask. For now, let's assume a steady state and continuous time for simplicity. Let's say we feed in an input sine wave of a certain frequency f, and see what happens at the output once steady state has been reached. simply plugging in sine 2 pi f times t into our original equation, which is this alpha times x of n plus b times x of n minus k, and we convert that to continuous time, we get the output is our gain alpha times our original sine wave plus our gain beta times a phase shifted or time shifted version of our input sine wave. It's the same frequency, but all we have is now a phase shift, which is based on TD. And remember, TD, we can work out our number of samples and sampling rate in discrete time. So this is interesting. We have two sine waves of the same frequency, but they're added together in different proportions depending on alpha and beta, as well as our phase shift. So this means, for example, our original sine input plus the phase shifted copy could be in phase, they could be out of phase, or partially in and out of phase. To visualize this a bit better, let's plot this on a graphing calculator. So we have our input sine wave, which is at a particular frequency f. We can play with the frequency. Let's just keep it at 1 Hz for now, just for simplicity. And we have a phase shifted version of our input sine wave, which this is effectively the output of a delay line. For this, it'll have the same frequency, but we can shift the phase or the delay of this other sine wave. Then we want to add them together with proportions of alpha and beta, so these gains. So we take alpha times our input sine wave plus beta times the delayed sine wave with this phase shift and see what happens. If I have no phase shift, so TD is 0 for the case of 1 Hz, and I have alpha is 0.5 and beta is 0.5, my sine waves simply add, and I get a perfect sine wave out, so we are in phase. As soon as I start shifting the phase or the delay due to my delay line, you can see the sine waves now partially cancel out and we get a lower amplitude at the output. Now if I delay even more and I have my input sine wave and my delayed sine wave 180 degrees out of phase, we can see that actually the output completely cancels and we get nothing at the output. So for certain delays, it seems like we get full amplitude at the output, then partially reduced, then for 180 degrees out of phase we get no output, and this cycle pretty much repeats indefinitely for increasing delay times. Also, you can play around with frequencies, alpha, beta gains as well, and I'll leave a link to this in the description below. We've already alluded through our time domain analysis to some interesting frequency domain properties and when certain phase shifts happen, what we might be able to get at the output. Now it's very straightforward by passing in sine waves and seeing what output sine waves they are in, for example, linear systems, but a more effective and direct method is, for example, by doing frequency domain analysis, and that's exactly what we'll do now. After which we'll then examine this on the real-world hardware again and then actually see how to implement these FIR comb filters. The frequency domain analysis is a bit more involved because we need to look at things as Z transforms. Please again look at the links in the description below, where some videos will guide you on how to use Z transforms in a very practical sense. I won't be covering this in this video. If you're interested, of course, stick along for these couple of slides before we move on to the software implementation and tests. Effectively, to get the frequency domain response, we need to convert our discrete time difference equation. So one you see at the top right here underneath the block diagram, we need to apply a Z transform and then convert that to gain and phase. Interestingly, once we take the Z transform, we can see that we have certain numbers of poles and certain number of zeros, whereas the number of poles is actually equal to the number of zeros, and that is equal to K. So how many sample delays we have increases the number of poles and number of zeros. Although this is very small, in the plot on the top right hand side, we see a pole zero map. We see that all the poles are at the center. So there's K poles at the center, meaning it's unconditionally stable. These poles don't move. And distributed around the unit circle, we have our zeros. This already hints at what the frequency response might be. To analytically get the frequency response, we can replace Z to the minus K with the Euler identity, so cos of K theta minus J sine K theta, and again, K is our time delay in seconds times our sampling rate in hertz, and theta is our normalized frequency, which is 2 pi f divided by the sampling frequency. You can really see if we multiply K by theta that our sampling frequency actually cancels out, and then rearranging to get the magnitude, we can get this expression in the center, which is the expression of the gain, so output amplitude divided by input amplitude versus frequency. This is square root of alpha squared plus beta squared plus 2 times alpha beta times cos 2 pi time delay times the frequency. This is already pretty interesting. Very simply speaking, our magnitude, our gain, is something to do with the square root of a cosine term. Cosine terms are repetitive, we have peaks and troughs, so maxima and minimas, so it'll be interesting to see what this plot looks like. And if you haven't already, you can see the gain and phase plot, our Bode plot on the right hand side. The magnitude plot starts at maximums, goes to minimums, goes up to maximums again, minimums, maximum, minimum, maximum, indefinitely up to the Nyquist limit. And this is where the name comb filter comes from. It's from the magnitude plot in the frequency domain, because this looks very much like a comb. Of course, changing alpha and beta values, the delay time will change the appearance of this comb filter, and we'll see that in practice later on. What we'd like to know now is, where are the peaks and where are the troughs? This seems very, very repetitive. It always seems like at 10, 20, 30, 40 Hertz. In this particular example, we have peaks, and then repetitively and equally spaced, we have these minima, these troughs. To do this analysis, for example, looking at where the peaks or the maxima are, that's where the original plus the delayed signal we had in our block diagram add completely in phase. So there's no phase shift, our sine wave input adds on top to our delayed sine wave. To find that, we want to find where the cosine term is maximum, which is equal to +1, so 2 pi TDF has to equal to some even multiple of pi. Therefore, rearranging, we get maxima when f is equal to n over our time delay. So for example, if we choose a 0.1 second time delay, 1 over 0.1 is 10. So for multiples of 10, for example 0, 10, 20, 30, 40, 50 and so on Hertz, we shall get maxima. And that's exactly what we see on the bode plot on the right hand side. So it's 0, 10, 20, 30, 40 and so on, we get our maxima. Same thing we can do with our troughs or minima. This is where our original and the delayed signal add completely out of phase. We get maximum cancellation. The same method as before, we are equating our cosine term to -1, rearranging to find values of f where we get minima. And this turns out to be 2n plus 1 over 2 times the time delay. So a bit more involved, but what we can see if we plug in, for example, time delay is 0.1 seconds or 100 milliseconds, then we get 5, 15, 25, 35, 45 and so on Hertz. Again, looking at the Bode diagram, at 5, 15, 25, 35 and so on, we get these minima. Keep in mind, the gain is dependent on alpha and beta. In this particular diagram on the right-hand side, I've chosen the special case where alpha equals beta equals 0.5. But let's play around with this before we move over to the software implementation. I'll also leave a link to this in the description below so you can play around with it in your own time. I've set alpha and beta up as well as a variable time delay, and we can set a sampling frequency as well. On the y-axis, we have the magnitude, linear, and on the x-axis, we have the frequency, linear in Hertz. So for example, for a time delay of 1 second, we can see we get peaks at 1 Hertz, 2 Hertz, 3 Hertz, 4 Hertz, troughs at 0.5, 1.5, 2.5, and so on. If we change the time delay, for example, to 0.8, we can see these peaks and troughs move. We can also, of course, play around with the gain. So as we change alpha, we can increase alpha, we can see what happens with the gain, and we can decrease alpha and see what happens with the gain as well. And similarly for beta, larger and smaller. So in this way, we can get different frequency responses simply by changing 3 parameters. We can change the delay time, and we can change these various gains depending on what kind of characteristics we want. But now let's go over to software. Back in STM32 Cube IDE, I've defined 3 defines where we can change these values to try and experiment a bit. We have the alpha gain, the beta gain, and our delay in milliseconds. I've just chosen alpha and beta to be 0.5, and our delay just to start with at 100 milliseconds. The initialization of the delay line is as before, and now we'll wrap a comb filter around our delay line. If you remember from before, effectively our output was simply just calling this update function, passing in the delay line struct, and our current input sample. What we have now, for the case of the comb filter, is that we take our current input sample, multiply that by the gain, add our delayed sample from our delay line, multiply that by the gain, and add those 2 terms together to form the processed output. So very, very simple. All we had before was our update function from the delay line, and now for the comb filter, we're multiplying that by a gain and adding that to some constant, the alpha gain, times our current input sample. And that's all we need to do to create a very, very basic FIR comb filter. Right now, for 100 milliseconds, I can upload this code and we can move over to waveforms. We'll start off with our square wave from our wave gen with a period of 2 seconds and then look at the input and output. Again, input is our yellow trace, which is our 2-second period square wave. And at the output, we now have our comb filter output. We don't have just the delay, we also have the current input signal times the gain. That's why we always have 2 peaks per transition in this case, or per input AC signal. The first peak, you can see in the center at 0 seconds, is due to our current input samples times alpha. The second peak is actually due to our delay line times beta, which is about 100 milliseconds after the initial transition. So we have initial signal on the left, and on the right-hand side we have a delayed signal, and this is exactly what we expect from our comb filter, and of course you can see the same thing on every other transition. Remember, this is with the high-pass filter in place due to the hardware. But this quite nicely illustrates the original sample plus the copy sometime later, in our case 100 milliseconds later. What we can do now is also use the waveform software to do a Bode plot. So we'll plot magnitude versus frequency in this case to see if we get this comb filter structure. I'm running this from 100 Hz to 1 kHz, and I'm using quite a lot of steps, so quite high granularity for this particular comb filter. This is because we want to capture these peaks and troughs, and we need quite good resolution to do so, otherwise they'll be missed in the measurement. Remember, these peaks and troughs are quite close together, and they only spread further apart the less delay time we have. So remember, for 100 millisecond delay, which is what we're having now, we should see peaks at 0, 10, 20, 30, so multiples of 10, and then troughs at 5, 15, 25, 35, and so on. So we need quite good resolution on the frequency axis. This is of course taking quite some time to process, but we can already see this very familiar class comb structure now. Remember, this is for alpha equals beta equals 0.5, so we get very large attenuation at these minima, and we get our maximum gain at these maxima. So roughly, keep in mind there'll be rounding errors. 210 Hz, we have a maximum. At about 215 Hz, we've got a minimum. 220 Hz maximum, and so on. So this is exactly what we expect for a delay of 0.1, and alpha beta equals 0.5. Let's just have a brief look before we move over to the guitar at looking at alpha is 0.8 and beta is 0.2 for the same delay of 100 milliseconds. Let's upload that to the board. And this is what the result looks like in the time domain, again with a square wave input, and blue is our output trace. Remember, alpha is 0.8 in this case, and beta is 0.2, which is what we expect in this case, because 0.8 is our alpha gain, which is our direct feed-through gain, which is happening directly on the transition, and then 100 milliseconds later, we're getting 0.2 times that original input signal, so that's why this is a smaller bump, and we get this for positive and negative going transitions in this case as well, just to show that alpha and beta control the pass-through gain, so to speak, and the delay gain. The frequency response is then of course also altered. We don't get this special case with alpha beta equals 0.5. This is alpha is 0.8 and beta is 0.2. And we get this rather different frequency response still with this comb-like behavior where we get far less intense minima and instead of this kind of performance. So let's see what this sounds like with the guitar. Now let's try a different combination, for example, a delay of 500 milliseconds, as well as an alpha and beta gain of 0.5. Let's see what that looks and sounds like. So as expected with our square wave input, as the gains are the same, we should get 2 equal value pulses delayed by 500 milliseconds. So one on the transition, which is our feed through, and then 500 milliseconds after that, we will get our delayed version with a similar amplitude. Now, as we've increased the delay length, we should get much finer resolution or spacing between our peaks and troughs. Now, I've set up quite a coarse resolution here, so of course there's some accuracy missing here, but what we can see that as we increase the delay length, our frequency domain comb gets squished together, very simply speaking. But now let's see what this sounds like. Thank you very much for watching. I hope this video was interesting and useful and showed you the start of how you can create your own delay-based effects very easily in software. In a future video, we'll then be looking at full implementations of digital delays, reverbs, and more using FIR as well as IRR comb filters and of course our delay lines. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any of the latest videos. Thanks again for watching, and I hope to see you in the next video. Bye bye.